Okay, thank you very much for all being here at this incredibly early hour of 10 o'clock and taking the effort. So I'm going to talk about some work that I've been working on over the past few years, or actually my former student Job Veldbrugge has been working on for the past few years, concerning caustics. It's an old subject that for a long time was not very much playing a role anymore in cosmology, although in the mid-1980s the Russian mathematician Arnold was working on this together with Zel'dovich in the two-dimensional context. But there, approximately, it stalled. Over the past year or two, we have managed to lift it basically to 3 dimensions. Given that this workshop is focusing on the analytical aspects of mathematical cosmology, I thought it was appropriate to talk about this. I could have given it another title, Catastrophes in Cosmology, which is a totally appropriate title. But given the fact that this caused huge problems with the archive, AstroPH, a paper of us was held up for more than 2 months by a moderator because he thought it was not serious science. And we had really to draw every effort out of the cupboard to finally get him convinced. And finally, a referee report from Monthly Notices that lifted it. I can tell you about it more at coffee if you want to hear the story. The work is actually emanating, so Job Veldbrugge, who's now at Perimeter Institute, has done basically most of the work, most of the analytical work. But before that, it started off with a sabbatical of Sergei Shandarin, and he got a PhD student of mine, Johan Hidding, to work on this in a two-dimensional context. So that sort of revived the topic. Now, to give you an impression what we will be talking about, before you get the impression it's going to be awfully, well, esoteric or far away from reality, what you see here on the background is actually one of the results that we got of the filamentary outline of the cosmic web that you obtain in an LCDM cosmology. And what you see in green-blue is what is called the A4 swallowtail singularities. So you would think it's a rather abstract concept, but you see that actually it provides a really striking rendering of the filamentary network, and not only of its overall structure, but also of its branching structure, basically its multi-scale structure. Actually, on this plot, not only what we found is that there's not only one kind of filaments, but there are 2 kinds of filaments, to which I will return later, and the other ones go by the illustrious name of D4 umbilicus. So I will explain what this basically means. These are the papers that have been devoted on this. One of them is in preparation, which is basically the comparison between real embodied simulations and the predictions of the cosmic web structure on the basis of the caustics. And the other 2 basically outline the analytical work on this concept. So what it all goes about is basically the question of connectivity, like what Sandrine yesterday addressed, the topology of the cosmic web. How do we actually get together not only, not only identify the walls and the filaments, but also their connectivity? And there are several ways, as we have seen, to describe these things. So when we look at the cosmic web, and here you see a rendering of the cosmic web taken from an embodied simulation in which we identified by means of a multi-scale technique the cosmic web, you see how complex the structure is. You see a huge branch, a huge artery, but you also see the branches into what these days is called tendrils, even into the low-density regions. By the way, this technique is borrowed from medical research and sort of adapted to cosmological circumstances. I've been asked a couple of times to give talks for medical people for some conference, so they want to have some enjoyment and some pleasure, so they get a cosmologist to tell something. But when you show them this, they actually think this is the arteries in the body, because it's exactly the same kind of branching structure. So when we look at the cosmic web, we sort of can identify 4 major characteristics, and that's all what we need to address. First of all, we are dealing with anisotropic structures, structures that have an ill-defined shape. Flattened structures, elongated filamentary structures, anything in between, compact nodal structures, clumpy structures, and they've all been connected in a web-like network. So there's a complex spatial connectivity. Very important, of course, is the multi-scale nature of this network. So it's not only on one scale. The complex thing is that you don't really have a scale, so you will have to deal with this. There's structures on a whole range of scales. And then, of course, as you see from over here, and this is a rendering of the local universe as inferred from the 2-mass redshift catalog by a reconstruction method based on those of Francisco Quitaura, and then further evolved with adhesion. You see that voids, filaments, and walls in the structure. And you see that voids actually occupy most of the volume. Around 80% of the volume of the universe is in voids, and that finally, in the same 3-dimensional reconstruction of the cosmic web in the local universe, this is the Piskus-Perseus chain, you see how complex the connectivity characteristics of this cosmic web are. So is there a way to understand this? So we could go to a density field or some other measures. Actually, over the past few years, we saw some very nice work that actually pointed out that the best way to look at this, if you want to understand the dynamics, is to do the full phase space analysis, to see the whole thing not only as it is in space, but also take either into account the velocity or momentum field, or if you translate this to the language that most cosmologists are talking about, Lagrangian space, the original positions versus the final positions, Lagrangian versus Eulerian space. If you combine those things, you get some very nice insights into what is actually the cosmic web, how is it defined dynamically. And that's what I have to finally, where actually with this caustic structure, I'm going to refer to. That's what I'm going to focus into. Again, coming back to some of the structure, I sort of showed you earlier on that rotating movie with only the filamentary network. This is actually the result. This would actually be the conclusion of the talk. So here you see the same box. And in the box, we identified basically the walls, which are red, the membranes of the cosmic web. And in blue, you basically see those A4 swallowtail filamentary features. You see, by the way, that there are some extensions in green, and they are the D4 umbilic features that you also can identify on the basis of the phase space dynamics. They are actually the ones, the filaments that are fully collapsed in 2 dimensions. It turns out that the swallowtail ones are actually only fully collapsed in 1 dimension, but they are the intersections between walls. So there's a distinction, and actually the A4 ones are the extensions of the D4 ones, and the D4 ones are actually then again connecting to the A5 nodes of the cosmic web. So you see this whole language of caustics and catastrophes, actually, as you see it over here, gives a very nice illustration of the geometric structure of the cosmic web, right? So how did we get there? That's basically the story of today. Yesterday, Mark already showed the phase space picture. I thought this was from Tomé Bell, but apparently it was from Stefan Colombi. I don't know. I should look this up. But basically what you see here is the evolution along 1 dimension centered on 1 density perturbation, where you very nicely see how in time, and here you see 4 time slices, the structure of the evolving peak is basically in phase space, making a wrapping structure. So you see that this is basically what happens. And notice what happens in terms of your space observation. When you look along this line, what you are going to get, according to this phase space structure, is of course, the reflection of the phase space onto space. And what you see is an accumulation of mass elements at distinct positions. Here there are 5 positions, and these are 5 streams, basically, identified in this region where you get peaks in the density structure. And that gives a far more accurate display of the density structure of the cosmic web. I will soon show you a very nice illustration from the work of Tomé Bell that basically showed this in a simulation. This was basically realized by 3 groups around the same time. Sergei Shandarin had a description in terms of tessellations, and he called it a phase space sheet. Tomé Bell and Oliver Hahn were doing similar work, but then on using a slightly different tessellation of Lagrangian space. And Mark Nyrink had his origami folding formalism that he described yesterday shortly within the concept of the spider web. Now, how you should see this in terms of the formation of the cosmic web is very nicely illustrated here in a sort of cartoon that Johan Hidding, my PhD student, made. And what you see here in blue is basically only in 3 dimensions of phase space, but you sort of can imagine this is an Eulerian of the Lagrangian dimension, and these are 2 Eulerian positions we can only see in 3D, so that should be sort of give the impression. And here this is the phase space sheet. And as things are evolving under the force of gravity, this phase space sheet is getting folded. But what you observe is basically the reflection in space. So what you're going to see is basically the following. So you see the folding of the phase space sheet, and at the same time you clearly see the formation of the cosmic web with its filaments, the filaments connecting into the nodes, and that kind of structure. So this is actually the way we should see the evolution of the cosmic web. Now, a far more detailed simulation on this was made by Oliver Hahn and Raul Angelo in the case of the warm dark matter scenario. They remarked that actually if you would employ the conventional n-body simulations, you would not be very successful because basically walls would fragment artificially into particles. You better do it in a phase space way. So Oliver sort of devised a code that would solve the full Liouville equation, and basically you get a beautiful rendering of the evolving warm dark matter's evolution. And let me show you this and look at what is going to interest us very much. You see the detailed structure, but look, it is as if you see the wrapping of a sheet, right? Look, for example, around that node. It's almost like you're wrapping up some piece of paper or something like that, and you see that it becomes more and more complex as time proceeds, right? So you clearly see that the folding structure there is very complex. You also see, when you look here, the very detailed stuff. You see that this is a filament, but also look at the edges where the things are nearing infinite density. And that's what we are going to look at. Can we say something more about this? So on the basis of this, you can basically say, okay, when I look at these features, and this is this n-body simulation that Tomé Bell and Oliver made, you see a very detailed structure. On the basis of these details, you can actually say, okay, how many times did actually matter streams pass through? Because as you saw in the folding process, as a result of gravitational clustering, you get the fact that matter streams go in and out, in and out. on the basis of this, you can actually identify or make an identification of the cosmic web based on solely and only the streaming, the number of streams that are passing through. So, for example, here, those are the regions where mass is still just going on, but hasn't met any other matter streams. So they're the one-stream regions. And arguably, you could say, well, those are the void regions, right? But once matter starts to meet up other currents coming from another direction, you basically get the three-stream regions. In 3 dimensions, those are the walls. The 5-stream regions, where things are coming from the other direction too, those are the filaments. And you can actually go on to an enormous amount of streams. For example, if you're sitting in those nodes, you easily get up to the thousands of streams, as you saw, the wrapping of these things. So you basically get a dynamical identification of the cosmic web. Now, how are we going to deal with this when we talk about building up and identifying the cosmic web, not only on the currents, but basically on the sheer dynamics? So we have to understand where those filaments and walls are emanating. And the agent of the formation of the cosmic web is, of course, the tidal forces. Yeah, Marcel?
Why is that the walls have only 3 streams?
It's basically that, remember this picture that I showed you before, the 1D thing? Yeah. It's basically this. So the walls are the ones where currents are coming basically from 2 directions. Yeah. So you basically get this. Yeah, so you have 1, 2, 3.
Even in 1D, then I fold out more.
That's a resolution, small scale power.
Then it's already in a higher than, in a more evolved state, right? So the agent for the formation of the cosmic web is basically the deformation tensor or the tidal tensor. So the tidal tensor, as you see over here, in terms of its density field, and this is basically a quadrupolar moment, and that in fact translates into a tidal force field, and the tidal force field takes care of the contraction of mass and of the anisotropic contraction of mass dependent on the signature of this tidal force field. When the tidal force field has 2 signals going inward and 1 moving out, then of course we get a filament. If we have 1 only in 1 direction and 2 going outward, then we get a wall. So you basically need to look at that. Here you see that basically if you do this constrained random field approach that Sandrine indicated yesterday, you basically set up, for example, a tidal force field that would have to evolve into a filament, as you see it does over there, and you automatically get 2 clumps on the other sides because they take care of the quadrupolar field, and that in the end leads to the cosmic web. So it's clear that we have to look at the tidal force field or the deformation field. Now the first order approximation in this sense was made by no one else than Zel'dovich. So this is what in first approximation we are going to look at. In the end, you may do it more accurately and go to higher order Lagrangian perturbation theory. But in first instance, we are going to look at the folding in terms of the Zel'dovich picture. Now, here's a picture of Zel'dovich. I think it's a picture that is not that often shown, but it's quite characteristic because he has some nice equations over there. And he looks here a bit younger than in the later pictures that most of the Western people know about. Now, the Zel'dovich approximation, of course, is a ballistic motion, and that ballistic motion is basically meaning that everything is set into motion in the initial instance, and everything in the terms of the structure is basically determined on the gradient of the initial Lagrangian potential, and the gradient of that basically determines, that is basically the tidal force field, is going to determine the nature of the deformation as a result of the streams that are going to be induced. So when you set this into motion, this was a simulation run by Johan Hidding, you basically see what is happening. You see the formation of the cosmic web. You also see there where matter streams are meeting up. You see the formation of, well, first of all, it looks artificial that things go on ballistically, that's Zel'dovich. But if you go slightly back, you see that there is nice structure around the walls and the filaments, the structure that we are going to use. I'll get back to that in a certain moment. The Zel'dovich approximation, in a sense, is therefore the ballistic motion, and but it suffers from the fact, of course, that it doesn't have self-gravity, so matter just displaces on, and ultimately can actually prove that this is going back to the fact that the Euler equation in co-moving coordinates basically is force-free, or actually the potential term drops out because of the transformation that you use. Now, when you look at this and actually use this displacement, you get, of course, a very straightforward prediction for the density field according to the Zel'dovich approximation, very well known. So you basically take the Jacobian of the displacement field, which is over there. That's actually the deformation tensor, which in the Zel'dovich approximation is directly proportional to the tidal force field that we already identified as the agent of the formation of the cosmic web. Important here is that when you look at this deformation tensor and then take its 3 eigenvalues, you actually get a prediction for the density with 3 terms in there, all dependent on the eigenvalues times the universal linear growth factor dt. So along 3 directions, you actually are able to cause a singularity to get full collapse that is reach infinite density, basically at the time when 1 is dt times lambda I, right? So this already immediately tells you that this kind of deformation field, displacement field, is leading to an anisotropic structure. So, what does this then finally lead to? Well, when you would look into that simulation of the Zel'dovich simulation, at a certain time, you actually get to see something like this, right? That's what you basically saw, although this is smoke coming from a pipe, but this is the same thing. This is basically a picture of, I thought it was smoke, and you basically look in one line, and what you see is that actually the structure is not only having this sort of continuous display, but it has these very characteristic singularities where the density is infinity. And that's what we call caustics. And the question is, can you actually identify these caustics and classify them? There are all kinds of features here. For example, here you see these sharp edges. Well, these sharp edges are what we call faults, right? And so you can actually see at the end of the faults, there are very sharp edges, and then you get cusps. And then there are all kinds of more complex ones, like over there, which are corresponding to the more complex caustics that are called swallowtails, etc., etc., etc. This brings us to a identification of the Zel'dovich approximation with something that we all know when in the summer you are near a harbor or something like that, and it's a very sunny day and the water is calm but not too calm. You see these very nice patterns on the sides of the ships, right? That's exactly the same thing as you see over here. Here is a glass plate, but the glass plate is not uniform, and because it's not uniform, the diffraction pattern actually leads to something that looks tellingly like something that you see in these simulations, or the prediction of the Zel'dovich approximation, right? And actually, when you go into the literature of caustics, overall, you won't find a lot on gravitation and caustics. Nearly everything in caustics is about light diffraction. That's where most of the focus of the study of caustics is about. In the Zel'dovich approximation, therefore, we have something similar. And you see here the similarity with this smoke pattern. See here the sharp edges, there where you had the filaments in the walls. And here you see the more complex wrapping, where you had wrapping from different sides. And so you see that in the build-up of this sort of Zel'dovich field, there are all kinds of sharp features that correspond to features in the cosmic web. So that's what we're after. What we are actually after, if you would look at it in 1D, is you basically could look what happens in the deformation of the Zel'dovich approximation. So you would have the Lagrangian coordinate, and you put that versus the Eulerian coordinate. You start up with a one-on-one mapping, but because of the gravitational evolution, you get something that looks like this. So you get the three-stream region, and that translates very nicely into a density field that's exactly like what you see over here. These cusps at the end that you see over there with an inner region over there, right? So that's the kind of structures that we're dealing with. These things were identified with a long time ago by some very well-known mathematicians. I will mention them in a while. And they got names. All these different wrappings got names. So let me introduce you those. The first wrapping is by far the most easy one. They are the ones where 1 is d times lambda 1. That's basically the first collapse. When you would not look at the density field, but look at the random field of the first eigenvalue, you could actually identify where this is going to happen at a certain moment. You're just going to look at the contour map and you say, well, you know, at this time, these guys are going to collapse because that's where d lambda 1 at that moment is 1. Then the other guys are going slightly later, then the other guys, and the other guys, etc. And it all starts at one particular point, which is, of course, the local maximum in that field. This is the Lagrangian map, but of course, when you would translate this to the Eulerian map, what you actually get is here, for the first time, a feature starts to emerge. The birth of a wall or a filament. Then gradually, what you get is that this thing is actually collapsing. Things are passing through each other, see over there. So you get here these edgy regions over here, and then you have tips over there. They're the cusps of these things. The Russians identified this as blinis, pancakes. That's where the name pancake picture came from in Zel'dovich times. And then clearly, you see that after some time, you get these features that start to look like these thick pancakes, right? Like these blinis. So this is actually what you see. The names, what you see over here, are actually 10, are actually the ones, 10, okay. Wasn't it 2/4 11? Yeah.
It has been 40 and then 30.
Ah, okay. Yeah, so these things here are basically outlining those features. So what you have to look at is the different eigenvalues. And here you see the different classes of eigenvalues for the different dimensions. In one dimension, everything depends on only one eigenvalue. In 2 dimensions, on 2 eigenvalues, lambda 1. And what you see is you can have collapse along 1 eigenvalue, but also along 2. Now, the ones where you have collapse along 2 dimensions, those are the D-class, umbilic ones, and this is the A-class ones. In 3 dimensions, it's even more complex. You have EA, D, and E. And inside these classes, you again have different things coming up. So what you actually, in the context of the build-up of structure, have to do is look at the landscape, not of the density field, but of the deformation field, and in particular, the eigenvalue fields. That's what you do. So here you see a contour map, and on that contour map, we drew some lines. So for example, this red line, that's the red line, that's the so-called A3 line, on which you see the emergence of the walls, and subsequently the spreading of the walls along these lines, right? So that's where a major part of the evolution is going to take place. This is 2D. In 3D, this will lead to walls. You can, in 3D, also go for an even higher order one, the A4 lines, etc., etc. So on the basis of that field, you want to know, where are these features? Can I actually tell where they are? Now, the problem was that these three guys who are seminal in this field, Zeeman, Thom, and Arnold, in particular Arnold, identified all these catastrophes up to 3D, but he did that in very complex mathematical terms that a cosmologist cannot really use in a practical sense. So you can look up these papers, it's beautiful. This guy had complex equations. He saw them in his head, but he probably was one of the few people on the Earth who was able to do this. Right. So there's a problem. We ended up with the problem that here we have all these different caustics and catastrophes, but we don't have a useful way to describe these things. Until Job came around. Job looked at this map, and he looked at that condition. That was the one condition that Arnold had defined for this A3 line that was useful. So we basically can identify this line where in 3D the walls are, in 2D basically the line, and it's very simple. This is actually the eigenvalue vector. So it's the eigenvector of the deformation field. And this is basically the normal on the eigenvalues. And you see that when these things are perpendicular, and you see this is actually true. Look at these little lines. They are all perpendicular to that line. So you can identify them, right? So you can have that caustic condition, but not in general. So what we did is basically try to write out in a more visual way what would happen with the deformation of this Lagrangian manifold as it would develop singularities. And in view of the time, I'm going to proceed a bit more rapidly, but you can actually very straightforwardly show that it's quite simple. This is the deformation tensor, eigenvalue tensor, but very interestingly, this is the eigenvectors. Now, anyone in singularity theory, Eulerian singularity theory, would tell you that the only thing of interest is the eigenvalues. But here it shows that in Lagrangian singularity theory, that's not true. This then is the tangential vector to the manifold, and basically means if you have the eigenvectors and you have the eigenvalues, then you can actually straightforwardly use this condition to identify all of the singularities. And this became an equation. This is basically the condition. So here mu I is the eigenvalue. I must say here is the mathematical definition. Mu I in Zel'dovich is minus d times lambda I. So it's just turned around, right? So it's the thing. So 1 plus that eigenvalue times the eigenvector matrix times a tangential vector to that singularity, that should be 0, right? So when you do that and put it in practice, it's actually not so difficult. Just to give you an example. The first one, the A2s, those are the surfaces that are collapsing for the first time. That's damned easy. That's all the points that at one point says 1 plus mu is 0, or 1 minus d times lambda 1 is 0. That's easy. And if you then take all the ones throughout time, you get actually the complete A2 manifold. Those are all the points that went through such a transition, right? So that's one. But the A3 one is a little bit more complex, because then on these A2 manifolds, you take your tangential vectors and you wonder which points on this manifold went through another one of these transitions. And then you actually find that the eigenvector, in the eigenvector field, the gradient of the eigenvector field, that the condition basically of the gradient of that field should be 0. So you can write down the equation. And so you see that when you have the eigenvalue field, you determine the gradient. You actually have your singularities, right? And when you then connect them all over space, in 3D, this is the walls. So it's not that difficult, actually. And this is the walls. This is the result. So you see, if you compare it to an n-body simulation that was put on top of it, it's not so bad. A4 is more complex. Now, A4 is even more interesting. They are the filaments in 3D. So again, you're going to play the same game. You take the A3 surfaces, the ones that were these cuspy surfaces, and then you fold again, and you look where this caustic condition actually applied. And then when you do your sums, you find actually that the in product of the eigenvector versus the gradient of the eigenvalue vector should be 0. So that's your condition. That gives you the filaments, right? So that actually is the condition for this thing, for this fold, for this guy over here in 2D. So you can actually write down those conditions, and in the end, you can do them all. So this is the A4s. So in the end, this is going to give me the full cosmic web. I will skip the umbilics. So what I get is basically complete identification of the cosmic web in terms of complete mathematical objects. So you see here for A2, A3, A4, A5, D4, D5, those are the umbilics where you have lambda 1 is lambda 2 is leading to this, this thing. The mathematical name is fold, cusp, swallowtail, butterfly. You have the different umbilics, and you actually get these completely physical identifications. Now, of course, in the beginning, we thought this is all abstract, so we're never going to get, you know, maybe it looks a little bit like what we want to have, but it's only approximate. Well, have a look at this. This is the 2D situation. This is at 2 different resolutions, the Lagrangian map. On the Lagrangian map, you see the red lines, they are the A3 lines. The dots are the A4s. And here you see the transformation to the Eulerian space. So you think, you know, they get stretched and things like that. With underneath the map of the density field, in this case, Zel'dovich. And as you see, if, for example, the lower resolution, the higher scale, it follows those filaments remarkably well. So actually, it seems to give you what you want. In 3D, it's of course going to be more complex. You get your filaments, nodes, and if you can do those umbilics, you can actually see that near the nodes you first get these very heavy, fully collapsed filaments, and then they're stretching in these ones that are basically the boundaries between walls. You can get the full inventory of the cosmic web. I think in view of the time, I should, one more. There's one more thing that I wanted to say, because actually, on the base of this, and this is basically only a movie, you can construct the full hierarchical evolution of the cosmic web. Because this density field was basically made at some scale. But you could wonder, you know, how is this thing going in time? And it turns out that actually the buildup of structures goes by merging of structures. Not only clumps, but also of filaments and also of walls. And actually in this language, we actually have the tool for assessing this. And here you see how. This is the contour map of the first eigenvalue. Here you see the contours around the A3 plus maxima. This is where you started to build up your walls. And then you see a saddle point in between that mountain landscape. So what's going to happen when you are lowering your level, and you're passing through a swallowtail, or through this thing over there? Then actually these things start to merge. And you get one wall that was made out of a smaller one, or you get two filaments that were made out of a filament. So actually you can play the game by going at different levels and making things merge into each other. And look how the hierarchical buildup of the cosmic web is. And I think I should just stop here by pushing a few buttons and then thank you for your attention. So here you basically see the evolution of those contours. So you're going basically to lower and lower contours. And notice here, you know, they're separate, and here they merged. And this is the Alarian picture. So you see that gradually you start to build up larger and larger structures. This is only the edges, but of course, in principle, you can build up this whole thing. This again relates to another idea, persistent topology. Yesterday it was mentioned too, but I won't go into detail. It's just a program that we have for the coming time, how to describe this merging process. So I hope that at least I convince you that catastrophes are a bit more than just the crazy idea of some nutcracks who so now and then write cosmology papers, as this moderator from the archive thought. Thank you very much.